We are now coming to a right understanding of what independence entails when we have three events. Independence is a rule of products, and it's a rule of products for every arrangement of intersections of these three events. Before we proceed to abstract and generalize it yet further, let's see if we can draw some elementary conclusions from this definition. So, to test our understanding, I shall begin by posing a couple of questions dealing with formal set manipulations of the events A, B, and C. You should pause the lecture when the question is posed and see by scribbling on paper whether you can come to an understanding of what is being asked and whether indeed you can make progress. At this point, you're going to be using set manipulations and the basic definitions: additivity, independence. So, without further ado, let's start with our setting. Recall, A, B, and C are independent events in some probability space if four rules of product are satisfied. All four are required if you want to conclude that A, B, and C are independent. We have seen, when we talked about independence in the previous lecture, for a pair of events, that a rule of products, say the first equation, the probability of A intersection B is equal to the probability of A times the probability of B, is maintained if one or more of those two events are replaced by their complements. In other words, the independence of A and B is equivalent to the independence of A and B complement, which is equivalent to the independence of A complement and B, which in turn is equivalent to the independence of A complement and B complement. What if in a setting of three independent events, we complement one or perhaps more of the events? We've already checked that rules of products are maintained for pairs. So our question here comes down to, what if we look at an intersection of three events where one or more of the events A, B, or C are replaced by their complements? This would be a good time to pause the lecture and consider, for example, the probability of A intersection B intersection C complement, and seeing whether you can find a rule of products emerging by manipulations. You will need to use additivity, you will need to use the definition of independence, and just a smidgen of common or garden variety algebraic factorization. When you're ready, resume the lecture. Very well then, let's begin. So we want to look at the probability of A intersection B intersection the complement of C. We immediately have recourse to additivity, though, to be fair, it is slightly concealed. Think of the event A intersection B as a new event. This event can be partitioned into two disjoint pieces. That portion of A intersection B that lies in C, and that portion of A intersection B that lies in C complement. Additivity tells us that the probability of A intersection B can be decomposed into two pieces. That probability of A intersection B intersection C together with the probability of A intersection B intersection C complement. Move the second of those to the right-hand side and you've got the identity you see in front of you. Where now? Well, naturally enough, on the right we have probabilities of intersections, and independence immediately allows these probabilities to devolve into rules of products. And so, by applications directly of property 1 and property 4 of independence, we replace them by products. We are now ready for just a smidgen of algebra. We have two terms on the right, and we find that the probability of A times the probability of B is common to both terms. Naturally enough, we factor this product out, leaving you in round brackets 1 minus the probability of C. Aha! But additivity rides to the rescue yet once more. C and C complement partition the entire sample space. And therefore, the sum of the probabilities of C and C complement is 1, or in other words, 1 minus the probability of C is exactly identified with the probability of C complement. And there you have it. A rule of products magically emerges again. What conclusion can we draw from this? Well, surely we can now go ahead and look at what happens if we replace, let's say, B by B complement and keep A and C, or A by A complement and replace B and C. But you, of course, understand that replacing A or B by their complements and keeping the others two unfettered will give you an argument on exactly the same lines, and a rule of products will emerge. The conclusion then is, if you have a rule of products of these natures, with 1, 2, 3, and 4, the 4 relations for independence satisfied, then if you complement any one variable, a new rule of products emerges. But if you start with this and you complement one more variable, let's say B, and you look at A, B complement, and C complement, again a rule of products will emerge. And if you complement it yet one more time, and you look at A complement, B complement, and C complement, a rule of products will emerge like a creature from the chrysalis. Right? Again, you have products emerging for all possible combinations. And therefore, here's the slogan. Intersection probabilities factor into products for any combination of intersections of independent events or their complements. The 4 basic results, the 4 basic identities which govern independence, will give you now a whole host of intersection probabilities. Very natural and very intuitive. If A, B, and C are independent events in the sense, in ordinary language, that they do not impact or affect each other, then replacing one by a complement or 2 or all 3 by complements again should not allow them to influence each other. And indeed, this is what we have discovered.